So today we're talking about special number sets. Perhaps the word is not that good, special number sets. I would call them important number sets. The most important ones in maths, which we tend to talk about very frequently. The first one is this n. In maths, when a set is important, we use a calligraphical notation for it. So we tend to use a capital letter, and there is a double line somewhere. So you might see this written as n with 2 lines here in the beginning, or you might see it as n written with 2 lines in the middle. And the textbook has chosen that notation with the 2 lines in the middle. Both are the same. This n comes from natural. So the word natural, the first letter we use for this set, this is the set of numbers we are first taught in school when we are very young. They will usually, we start with 1 actually. They say 1, 2, 3, 4, 5, 6. It just carries on going on forever. So we call this an infinite set, because basically the number of elements in here, which is, as we saw yesterday, we can call that n brackets. That means number of elements inside that set. It's infinite because it carries on, goes on forever. Okay, so keep in mind that 0 is included in this set, so we start from 0, 0, 1, 2, 3, etc. In fact, if you go to university, you'll find out the type of infinity this number has, this set has, is a special kind of infinity. It's one of the basic and simple kind of infinities. Something very interesting about infinity is that there's not just one kind of infinity. This is way beyond the spec of what we need to know for school. You don't need to know this, but basically there are different types of infinities, and this is pretty cool. When I first found out, I was like, what? There's different types of infinities? I thought infinities is one thing. But anyway, this is like the first type of infinity we encounter. And this is 0, 1, 2, 3, 4, 5, 6, etc. It carries on forever. Then we've got this set. So let's start by this. This was set n. The next set, it's got this capital letter Z. Now, annoyingly, in English, this makes no sense why we call this Z, but I've looked this up because I'm a bit of a geek, and this Z comes from the word Zahlen, which is a German word which means number, apparently.
I thought it was because it looks like an N sideways.
Ah, right. Well, that's a good interpretation, but unfortunately, I don't think it comes from that. It comes from this German word. Basically, this one is very similar to the previous set. It just includes the negatives as well. So one way of writing it down is that you got 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Or you could think of it as ... and then you get to minus 3, minus 2, minus 1, 0, 1, 2, 3, and then you have ... So if you like, it goes in both directions. You've got the negatives and you've got the positives as well. That's pretty much the idea with this one. Integers is the proper name for this set. Often you will hear people say, oh, whole numbers. So I'm just going to write it down here because whole numbers seems to be the preferred approach for people, but actually the proper name for it would be integers. Okay, now here, if you put a little cross next to it, a little plus sign, this means we will only keep the positives from this set. So 1, 2, 3, 4, 5, 6, etc. So without the negatives and without 0. Okay, so basically we've seen n, we've seen z. Now we move on to this new set, which is q. So q, once again, unknowingly, you might think, where does this q come from? The q, and we usually have it have some kind of calligraphy here. This is how I do it. I put this vertical line here. The textbook has done a bit differently. You know, it doesn't really matter. As long as it's a bit calligraphical and it's a big letter, capital letter, then you're fine. This q comes from the word quotient. Quotient, which basically means something like ratio or fraction. You know, these are the ideas behind this. Ratio, fraction, you can think of it as fraction. Quotient is a number which comes up in division, is the result, let's say the result you get from division without the remainder. But anyway, this is related to division, this q. And why is this set called q? Because now this set is all the previous numbers, but also we will include fractions. So here, for example, you also have 2/3, you might have minus 11/4, you might have 27 over 1001. You know, all of these.
But it's only fractions, or like 1 is as well as q.
So here you include fractions and decimals, but decimals like 0.1, because 0.1.
So we don't include whole numbers.
Also whole numbers. So this one, if I were to draw an image, I was going to do that in a bit, but what I'll do now is just to show you, if I draw a little Venn diagram here, a little diagram on the left, then what you have in the very middle is natural numbers. But then outside the natural numbers, you have the whole numbers, the integers. So I'm going to put a little Z around that. Then what you have is around that, including the previous set, you've got rational numbers. So that's Q. So you've got all of the whole numbers plus all those fractions which do not simplify to a whole number. Because really any whole number can be written as a fraction. Like 5 can be written as 5 over 1. 6 can be written as 6 over 1, etc. So here, this includes the previous set and is called Q. Okay, now, interestingly, for those who are geeks, this N, the Z, and the Q have the same number of numbers, the same kind of infinity. So if you wanted to blow your mind, you can look into this, but basically this set and this set and these sets, they have the same amount of numbers, although it looks like this one includes the previous one and this one includes the previous one. So interestingly, this is a bit mind-boggling, but these three are the same kind of infinity. And now we move on to the final set, which is the set of real numbers. Okay, so this is perhaps the most important set to remember because this is really, for most people, the only kind of numbers they will ever get to know, unless you do IB high-level maths, in which case you'll probably find out about complex numbers. But anyway, keeping it simple, here we're talking about the real numbers, and the real numbers I will put as the entire diagram here on the left. So the real numbers are everything. So what do they include as well? They include irrational numbers as well. So irrational numbers, although the word is a bit confusing because we think rational probably means something to do with logic, reasoning, that sort of thing. So irrational might be like crazy numbers, but actually no. Here we've got to include irrational numbers, which means irrational numbers are numbers which you cannot write down as a fraction. So you can't write down as a fraction which has whole numbers on top and bottom. So for example, you will include pi, which as we've seen is 3.141592653589793233846. It just carries on forever basically. So this number carries on forever and you can't write it down as a fraction. The square root of 2 does a similar thing, basically carries on forever. Then you might have combinations of these like 3 root 2 and then maybe plus 5 root 3. You could have something like minus pi divided by the root of 2. So all of these numbers really, numbers which if you wrote down as a decimal, they would never end and they don't have a way you can write them down as a fraction. So that is real numbers. It's all the previous ones plus all of those weird numbers that you can't really write down ever. If you started to write it down, you would never end. Basically here, this is the real numbers. And let's now move on to an example of what we need to know when it comes to these sets. So they might ask you something like this. 2 belongs to this set. 2 is an element of this set. Remember? True. It's true because this is the whole numbers, integers. So yes, it's true. Okay. So we could say true that. Okay, moving on to the next one. The second one is in the rational numbers because rationals, these are fractions. So if it's a fraction, what you've got, then you can include it in these numbers. So fractions or decimals which have an ending representation, which ends, like 2.3, for example. Okay, so 2.5, basically you can rewrite as 5 over 2. So because you can write it down as 5 over 2 and both of these numbers are integers, then yes, it's true. So we can include that. Now the third one says this 5 is not an element of the rational numbers. Well, this is wrong because you can write, like we discussed earlier, any whole number can be written as the number divided by 1. So that means you can include it in those rational numbers. So this would be wrong because it says it's not included. Pi is in the rational numbers. Well, actually, this is not true because even though you would say, oh, I can write pi as pi over 1, but actually pi on its own is not a whole number. So this is not a whole number. So you can't really include it in the rationals. So not an integer, basically. Okay, so let's move on to the next one. This is wrong. Final one, minus 2 is not in the real numbers. Well, actually, you will never encounter a number which is not a real number. So if you ever see something like this is not a real number, then you will say it's wrong, always wrong, because all of the numbers that we will ever see, the entire set of numbers, the universal set here, will be the real numbers, unless you do IB, high level maths. So until we get to that stage, then you will always have a real number.
Sir,
Yes.
pi is a real number.
Yes. So pi is an irrational number, but it is a real number because all numbers are included in the real numbers. So basically, if we go back to that little diagram here, all of the numbers here are the real numbers, the whole thing. Basically, the box. So outside the red circle, if I create a new set there, just to write down what lives there in a way. So I'm going to use, let me use orange for this. So here we have the irrational numbers. Irrational numbers. We don't really have a symbol for these, or we don't tend to use it much. Basically, there is a notation which is R if you take away Q. So basically, we don't have a symbol on its own. It's like we say, if you take the real numbers and you remove the rationals, that's the irrational numbers. So pi lives in there. So you have pi, you've got the square root of 2, you've got minus root 3 plus root 5. So all of these numbers live outside this red circle of the rational numbers. But they're all real. All of these are real. So yes, let's keep that in mind, and let's now move on to another example. This is pretty much what you need to be able to do, guys. Just answer some questions like this. And then also we've got a different thing, one more thing to talk about today, which is how you would rewrite a recurring decimal as a fraction. It says here, show that 0.36 recurring is a rational number. So I'll show you a trick quickly here, which is going to be, if you have a number with a repeating decimal interpretation, if they give you something like this, 0.36 recurring, which will often, you'll either see it with a bar on top, or you might see it with a little dot on top of them. These are both equivalent notations. I'd say the dots are used more in the UK, the bar is used more in a lot of other countries. So here, basically you see this is really 0.36363636, and just carries on forever. So what we do in this case is this. Firstly, we call this number something like x. So let's say this is x is equal to 0.363636, and just carries on forever. And then we just notice that this number has 2 repeating digits. So because it has 2 repeating digits, when it has 2 repeating digits, we use a trick. We just multiply by 100. You're like, what is happening? I will explain. So we multiply this by 100. So what does that give us? It gives us 100x is equal to 36.363636. So basically, if you multiply this number by 100, the decimal will just move 2 places to the right, and you just end up getting 36.363636, etc. But now look at what we can do between these two numbers. What we can do is we can subtract the bottom number from the top one. So you can do 100x minus x, which means 100x minus 1x, and that gives you 99 lots of x is equal to, and then what do we get on the right hand side? So the thing after the decimal will disappear, because all of this is the same as all of that, because it's always thus 36, 36, 36, 36, just carries on forever. So
the final answer will be 36.
Yes, exactly. Nicely done. So 99x is equal to 36. So we can write x as 36 over 99. Which means we can write that x as a fraction. But let's simplify that fraction before we talk about the final answer here. So if we divide both numbers by 3, actually I think we can divide by 9. If you divide both of them by 3 though, you get 12 over 33. But then you can actually divide by 3 again, if you notice it. And then you can simplify further, so you get x is equal to 4 over 11. So that is the final answer. So what does that mean? It means that this number here with a 0.36 recurring forever, it gives you 4 over 11. So what does that mean? It means that this number here is a rational number. we can write it down as a fraction. So there is a group of never-ending decimals which are actually rational numbers. So you can write them down as a fraction. And those are the recurring decimals. So if we go back to this diagram here, normally the never-ending decimals go outside the rationals. So in here, if I were to write this down in orange, normally you have here I'm going to call it never-ending decimals. So these decimals are in there in the irrational numbers. But actually, there is a group of fractions, of decimals, if you like, of never-ending decimals here, which are the repeating decimals. So here in the rational numbers, we've got included the recurring decimals. So these recurring decimals, as we just saw, the little trick, they are rational. So keep this in mind. You can always write them down as a fraction. A classic one perhaps would be 1/3, which becomes 0.33333 recurring. So for example, other examples here would be 1/3, which gives you 0.3 recurring. Other examples would be 2/3. 2/3 is 0.6 recurring. I'm not going to do 3/3. I'm going to let you discover that on your own. But basically, any number divided by 3 will do this. There's all sorts of numbers that would do this. In any case, that's what I wanted to say for today. So I'm going to stop the recording here, and I'm going to give you some time to practice. And obviously, I'll be here to guide you and help you if you get stuck on anything.